The general idea is you go through a suspended bridge with the elves. We're looking at a rope that has two knots. One is called a head and the second one is called a tail. Okay, we'll use that. If you move the head away, the tail follows. Whenever the head moves, the head and tail are still away only by 1 pixel, let's call it that way. The tail doesn't move. If we move the head one up and second time up, the tail will follow diagonally. That's the whole idea. Ah, yeah, the gist of the puzzle. So the gist of the puzzle is that whenever we move those two, we're tracking the position of the tail, or rather the distinct positions of the tail. So even though it was a few movements here, the tail didn't move, actual distinct position is only 1. Let's take a look at the code. Before we go into tests, I think it's worth looking at the types that I've created for this solution. First, we've got a point, then we've got our most interesting and most important type currently, which is short rope, which only has the head and the tail. You can probably guess from this type that it's from the second part of the solution or the second part of our task today. And we'll be dealing then with a longer rope, which actually has few tails, or rather few elements of the tail. Then we also have the movement of the head, and the movement contains only of the direction which we are moving to, so it's left, right, up and down. In the move itself you also have the amount or how much you want to move, because our disposition will tell us that we want to move up 4 fields. And exactly as you can see, it's go right 4 times, go up 4 times, whoa, go up 4 times, go left 3 times, and so on and so on. Now, the first test is actually reading those inputs correctly. Next test is actually dealing with a single move of that rope. So we're starting with the rope that looks like this. Then we tell it to move only 1 position to the left, and then this is the position of the tail that we expect it to be. And now we test the overall functionality, so how many positions that was the tail at. For this particular input it was actually at 13 distinct positions. First function is read moves. So to remind you guys, this is the line you would be parsing with this function. So it's the U space and 4. U will be transposed to up, space will be omitted, and then 4 will be transposed to the amount in that move. Single move point accepts the point itself and the direction in which we want to move. We'll be using this single move point to actually move the head. The logic behind moving the tail is quite different actually, because the tail only follows the head. It doesn't really move on its own, it doesn't really care about the direction in which the head is moving. What we accept is the current position of the tail point and also the current position of already moved head point. We calculate the distance on x-axis and y-axis, then we calculate the new position of the tail, or rather the new x position of the tail. Similarly, we calculate the position of the tail on the y-axis. We grab the distance in x-axis and y-axis, but we make sure this is the absolute value of that distance. If one of those distance is equal to 2, then we actually move the tail. However, if both are 0 or 1 or whatever combination of those two, we don't move the tail at all. In the first version of this function, the logic was actually quite different, but this logic is already influenced by the second part of the task. Let's bring back my trusty head and tail. For the first part of the task, since from this position we can only move up or to your left, we will never actually end up in a position. where the head is moved 2 points on the x-axis and 2 points on the y-axis. This is impossible. However, in the second part, we unlock this ability. So in the second part, this move will actually be possible. Now it's not, so we probably shouldn't care about it, but the solution is already influenced by the second part, so I wanted to point that out. Next, we'll take a look at the single move short rope. Now we will be actually using those functions we saw a moment ago. First, we grab the head of the rope and we move it 1 step of the direction. Now we actually have the old position of the tail and the new position of the head. So we get those 2 positions into single follow point movement function to calculate the new position of the tail. After we have those 2 new positions, we can return a new short rope. Now we need to compound this movement by an X amount. By using this list, we force the next function to be run the exact amount of times. Map fold is amazingly useful when you want to have a temporary state that is pushed through the list. Why do we need the fold part, the accumulator part in here? Because the rope will be moving each time. So each time there's actually a new input to the function. We need the whole rope only to calculate the positions of the tail. Since the tail can actually stay in the same position for quite a while, we run also distinct in here, so we can have only distinct positions. Now to compound this whole knowledge together, what we do in how many positions was tail at is as follows. First, we read the moves from the input. The initial rope always starts in the same position, where the tail is at 0, 0 position and the head is actually on top of it, also at 0, 0 position. To get the tail positions, we start with moves array, then we run map fold once again, because one move short rope, it's still the single instruction, still the single move, and we have few of those moves. So we also need to compound the rope position between the moves, not only inside the move but also between the moves. Now that we have a list of positions of the tail, we can just check out how long it is to have the answer. How many positions was tail at? Alright, tests are green. We're done with part number 1. Part number 2. I already mentioned we'll be dealing with a longer rope. This time around, we do still have a head of the rope, but we also have few different parts of the tail. Actually, 9 of those. Now the movement is very much different because we're once again interested in the very end point of the tail, and it's gonna get dragged quite a lot, right? So if the head moves like this, the last part of the tail actually stays put in the same space. Since there are 10 links of the tail or 10 parts of the tail, we actually move only when we go with the head like 10 spaces right or 10 spaces left. So only here we actually start moving the tail. It's kind of hard to show. Most importantly, and this is what I learned the hard way, even though the author actually mentions it straight ahead, be careful, more types of motions are possible than before. Now, since the movement is compound, it's actually possible to move away 2 fields on the x-axis and also on the y-axis at the same time. Now we're gonna need that long input as a different example. Here is also that test for the long rope example. Most importantly, we've got those 2 new tests that operate on the longer rope, and they operate actually on two of those inputs, the first one which was shorter, and also the second one which is longer. Not longer as in more moves, it's actually the moves are longer in the amount of them. So what really changed in regards to the solution? There's only 3 new functions here. First one is single move long rope. Starts very similar to the single move short rope, because we're grabbing the head of the rope and we're moving it into the direction by one field. Then we have to remember that a single move of the long rope is actually a series of single short rope moves. I'm gonna need a third hand. So this time around, imagine we've got a head and 2 parts of the tail. If the head moves to the left, then the first part of the tail follows to the left. And we can take a look at tail number 0 and tail number 1 as another short rope. Its head moved to the left, so the tail also follows. And this is exactly what I did. So I run another map fold. So I've actually got 3 levels of map fold here. First is between the moves. Second is within the move, between each particular repetition. And then the third level is actually between the long rope on a single move. So long rope is treated here as multiple short ropes, and then we once again compound that movement with map fold. The whole idea for the how many positions was long tail at is very similar to the previous one. The difference, however, is we create the initial rope differently because it's the long rope, and in here we accordingly use move long rope instead of move short rope. Everything else is the same. We've got map fold, we've got the first because we disregard the long rope at the very end. We also have the list of lists of points, which illustrate how the very end of the tail was moving. So we once again compound this, then we run distinct on it, and at the very end we are only interested in the length of that tail positions list. Phew! That's actually hard to describe somehow. Let's actually run the thing. And here you've got your output. Alright, thank you a lot. I'm very happy you've been here. Please consider subscribing if you want. And till the next day. And as always, guys, we can do better as a pack. Bye. I forgot to set it in the last video. And you pretty much need to take care about... what? I don't know. And then in the move itself you all and this, what is it? It's not a sound bar, it's a speaker. Alright. Now here it is, how reading is important, kids.